right, I think we're up. So hey everyone, so today what I want to be talking about is this guide called the System Design Primer. So I'll have like links to everything in the description below, but essentially this is like a really useful reference if you're preparing for any sort of like system design question, where it's like, well, how does Twitter work? How does Instagram work? How do you implement a queue? How do you implement a file system? How do you implement a URL shortener? So I think the purpose of these questions is to just sort of test like your basic understand how all this stuff works. Like you may not like, I mean, obviously you're not gonna have time to implement all of these things because like there's entire companies implementing this stuff. But you should still be able to speak at a high level how this stuff works, and you'll notice that there's like sort of a few common ideas that show up quite a bit. Like one, for example, is like a load balancer where you're distributing work over several nodes. Another one, for example, is like a cache, and then a cache with like read replicas versus like, yeah. And then another one, for example, is queues, where essentially if you're passing data from one system to another, but there's a lot of data being passed in, the way you pop it in and back out is queues. And another one, again, is like sharding, and then federation is sort of another similar ideas. So these are sort of like the themes here. And if you want like good, like comprehensive explanations of what all this stuff means, I highly recommend this book, like Designing Data Intensive Apps. It's like if you're like hardcore databases person, this may be a simple book, but if not, then I think it's invaluable. It actually explains how a lot of this stuff works, like some trade-offs with relational versus NoSQL, how the message brokers work, what's up with stream and batch processing. I thought this was one of my personally favorite tech books ever, and probably my favorite O'Reilly book, to be honest, even though it's not even in machine learning. Yeah, so I'm sure you'll enjoy it. Another reference I'd really recommend is this one. So this is called The Architecture of Open Source Applications. And what's interesting about this book is that it takes like actual open source apps and then shows you how they work. So for example, like let's say we want to look at something, I don't know, it sounds cool. I don't know, LLVM, right? So this was actually written by Chris Slatner, and then it shows you, well, like here's like what the IR looks like. Here's all the components. Like you have the optimizers, some like front end and back end, depending on the language, the libraries, and it gives you like a pretty good idea of how this stuff works. Just because, like, unfortunately, there aren't textbooks about most of these topics, like because they're new. Some there are, like let's say there's a lot of books about Git, but overall it is just very hard to find this information unless you yourself go to the GitHub repo and try to build like a flowchart diagram from it. That's why I really like this book, and I've like skimmed it quite a few times over the years. Like Audacity, for example, is like a music processing library, so it shows you like okay how the UI works, how the recording and playback works, just straight up invaluable. So if you have time, definitely make sure to check this out because it goes beyond just like I think the sort of web aspect of system design, which I feel like a lot of the at least the tech interviews I've seen at bigger companies, so think like the Fangs, tend to focus on like sort of a web app. Like, what does it mean to deal with lots of concurrent users? But I also think these are very interesting because, like, let's say stuff like music processing apps or game engines, like these have lots of moving parts that all need to move really fast. Otherwise, the software is sort of unusable. So again, these are all invaluable. So make sure to check it out. The architecture of open source applications. But the reference I want to check out today is this one, right? So let's say, for example, here, like it's not entirely clear what this is a system for, but it looks like some sort of like web server where okay, well, you have a client that uses a DNS server to figure out where the website is. And then, you have a content delivery network, so it can like basically cache in requests by the user. Otherwise, once the user makes a new request, it goes into this load balancer, and there's several of them here because there may be several load balancers distributed across regions and geographies. This makes a call to some sort of like web server. Again, this is sort of a replicated entity. Uh, and the kinds of requests a client can make can either be read requests or it can be write requests. And in the case of a write request, it could be async, in which case like that's where you need the queue. And then the queue basically popping from this queue gives it to sort of worker service, which then can read and write to either a NoSQL database. So for things like logs, but if it's stuff like user data, then this wants to go to a SQL server because you want the transactions to be ACID, as in like you want it to be there and not have like object like data corrupted. And again, here with the sharding and federation, like these are just sort of generic techniques where you can split data based on some properties of the user. Like let's say here, for example, this is splitting based on like the customer name. Let's assume first name, whether it goes from A to M or N to Z. But this could also be based on, let's say, the kinds of streamers you watch, or it could be based on your geography. And then federation here is a different idea. It's basically, you have your customer data, you have your product data. So these are all like very different kinds of data sets. So it makes sense to have them be in different places. Let's see. So what is this? Anki flashcards. I'm personally not a fan of Anki flashcards because I feel like memorization is sort of overrated. I think sort of being able to rebuild stuff from first principles is more valuable to me, at least. At least I feel like ever since we have Google, like memory is sort of overrated. But anyway, like this is sort of a similar service here. Let's see what this goes. So this goes over a whole bunch of stuff from scalability, performance, latency versus throughput, availability versus the cap theorem. So we'll briefly talk about this: availability patterns, CDNs, load balancers, reverse proxies, application layer database, caching, which is a huge topic, async communication, and security with some appendix, right? So let's see. Theme per breadth and long, load balancer. This is kind of interesting. Yeah, I like this. There's also some design review question. Okay, this is fine. All right. So I guess like this is sort of interesting, right? Like often when you're thinking about building a system, you need to think about like who's using it. So there's sort of some constraints that automatically determine what you're doing. Like for example, if you're I don't know, you're sorting some data, but you're only going to be sorting 10 elements at a time. Like there's no real reason for you to even be using merge sort. You should just use like brute force sort, and it's probably gonna be faster. So basically, how many users there are, like how much data you should handle, how many requests per second, like all these will dramatically influence things. So you can't just like take in the sort of like naive big O characterizations and assume it's infinite scale. Like sort of be hacky, get things done, and only build things for large scale when you absolutely need to. That said, some system designs make it easy for you to scale in the future, and that's definitely another thing you need to consider. So with the high level design, you sort of need to sketch out the main components and connections. So there's a few recurring ones, right? Like let's say, so going back here, things like a memory. Oh, this is a Twitter service. I see. So yeah, like in the case of a Twitter service, like the client, the load balancer, web server, there's the read, write, search API, the timeline service, the memory cache, etc. Uh, at least the memory cache, object store, and the SQL replicas with the master slaves, like this is gonna show up a lot. So make sure to just know this pattern. And then I guess like whether you're a read pattern or a write pattern, the Fanout service is interesting because the write API has an impact on a couple of things, right? Like the notification service, the search service, user graph service. So it makes sense to have another service whose entire like existence in life is to just make sure that data gets rerouted to a bunch of places. This is sort of similar to like an idea like a queue, but it's different from a queue in that like once something is popped, no one else can see it. And so this is why this fan out service is here. Yeah, whereas like the read API, like well, there's a couple of stuff you could read. Like if you're on the homepage, you're mostly reading tweet info. But if you click on a tweet, like now you're in the user info land, so the request is a lot more specific. Whereas here, there's probably even within the timeline service, like you don't just get a tweet. Like there's a to generate this timeline. There's some sort of ML algorithm that's also using some user data that's from here. So there's a couple of connections here, obviously in the real Twitter app, like are missing here. But yeah, I think this sort of gives you the overall idea. So let's see. Um, Another thing that's interesting is like once you have the boxes, it's useful to sort of discuss things from a like, well, what does the system need to do, right? So sort of in English, like let's say URL shortener, it needs to generate hashes, which means that you can't have hashes collide. And then the question is like, well, where do you put these hashes so that you make sure they're not being stored? Like, should this be in a SQL database, no SQL database, key value store, whatever? How durable does this need to be? You know, is a hash guaranteed to be unique for all of its lifetime, or only for like a couple of days, because that will influence your constraints and your costs. Like, are you a one person started building this, or like are you a giant company? All these are things you need to think about. And then scaling it, I would say these are sort of like the main ideas, right? So you have the idea of horizontal scaling, which is distributing the distributing. So let's and then load balancers, which lets you horizontally scale. So these sort of usually always come together. Caching is also like a critical idea, because you don't want to go through all of your data. There is a sense of like what is relevant, and sharding is just like a way for you to basically split up data. So as a like it's sort of it's like another form of horizontal scaling, and that here I think they're mostly referring to compute, but here they're talking about storage. And I think one that's missing, that's very underrated, is vertical scaling. So that's the idea of just getting more expensive machines. So let's say I don't know, your Stack Overflow, right? And Stack Overflow was able to run their entire service with like 30 machines on SQL Server. So the fact that that maybe you invest a bit more in having some machines, and instead of having to manage a cluster, thousands of machines, you only need to deal with 30. That's a lot simpler to reason through. It may not be what Facebook should do, but if you're like, let's say, I don't know, basically if you're anyone who's not a hyperscaler, often I think vertical scaling is great, and then horizontal scale when you start getting diminishing returns. Um, so yeah, so there's a couple of useful references here, and so I guess now uh, let's see. So let's just pick like two or three interesting ones, right? So design that systems that scales to millions of users on AWS. Okay, that seems interesting. The data structures for a social network. Okay, that also seems interesting. Okay, let's look at mint.com. So this is a personal finance app where you can link in your different investment accounts and your bank account just to see like how much money you have and how much you're spending, and etc. Let's look at also how to design a system that scales to millions of users on AWS, and then let's look at like URL shortening, right? So, well, let's see. So first thing here they're doing, okay, so they're following the same framework that they were before, as in sort of figure out like back of the envelope calculation, like, well, what's happening here, right? So user enters a block of text and they get a link. And then the setting does not expire, and then you can make it set so that it expires so that you can reuse some of the data. Although it's questionable here whether any user would do this, right? Like only a system would care about this. A user by default would just do this given the choice. So the user is anonymous, as in, so we're not going to have a database that keeps track of people's emails. We also want to, like we want to know how popular our service is. Let's say to estimate how much money we can make off of ad spend. So you could have like some basic analytics on the website. The service can also delete expired tweets, and it has high availability. All right. So what stuff that's out of scope is that registering for an account, the user can set the visibility and can set the short link. All right, this makes sense. Like let's say if the user can set it, really what you need to see if it's available, right? First, and if user setting the visibility means there's some sort of notion of users, right? Because if only certain users can see it, that means they need to log in. So since we're not registering people, like this constraint automatically follows, right? And so you can sort of assume that traffic is not evenly distributed. So for example, here, what this means is that like you could have spikes. Like the most famous one is around the holidays. So think stuff like Black Friday, Christmas. Like these are holidays where like typically website usage balloons. So something you need to consider. You want to work with tens of millions of users, 10 millions of writes, 10 millions of reads. But more people are reading than writing, and that sort of makes sense, right? Like, because after you put a short link on your website, you would expect more than one person to check it out. Otherwise, it's like really, what are you doing? So some of the back of the envelope calculations help here, right? So you could have like, how long can the total website be? Like, let's say it can be at most about a kilobyte. And then if it's a kilobyte and then we're assuming 10 million pastes, that means that there's about 12 gigs of paste content per month. And then 450 gigs of new paste content in 3 years, which is good because let's say for at least the first year, you just need to buy like a single SSD to keep track of this. So that's a good way to estimate the costs, whether you're doing this on-prem or on something like AWS. Uh, And then this is an interesting guide, right? So like one request per second, that's 2.5 million a month, and then 40 per second is 100 million. Okay, sure. So the high level design, like let's sort of think about it, right? So you have a client, and then it's gonna go to the web server, and then either it's gonna read a certain URL, in which case here you're gonna make a call to a SQL server, which is then gonna return back the actual URL that you need to that you need to go to. So just fill it up in your browser. And then, so yeah, so this is what the write does, and then the object store, and then the analytics here is basically just to make sure, well, let's say every time someone clicks on, basically, every time someone writes, that's a usage, like that's one new user. And every time a short URL is used, that's also another usage. So you would basically segregate those two things, and that way you can count, and then you can validate the 10 to 1 ratio that they talked about earlier. Right, so basically the here, like basically they're sort of describing it in text, for example, in this case. So they're saying, okay, well, check if the URL is unique. If it's not unique, generate a new URL and then save it to a SQL database and save the paste data to an object store and then return the URL. So this is sort of what we talked about earlier. And so here, for example, instead of using, like a NoSQL data, you can just use a key value store here. So something like Redis would be ideal because it's really just the key is the short URL and then the value is the long URL. So in this case, it's very obvious what it should be. Whereas if you did have users, then having stuff like the username, the password, more data would be useful. But if you wanted to have a, like let's say that's one. But if you want to have more data, you could have, for example, like a paste, like a paste event would have the actual URL, which would be, let's say, in case it's short, it would be at most 7 characters, right? So I don't know how many characters there are total in Unicode, but let's say a lot. And then 7 times that would just give you the total range of URLs you could have at any one point in time. So the expiration link, the create date time, and then the paste path. So in this case it's a lot longer, but it's a variable length, right? Because some URLs are short, some are long. And then a primary key here. So they're saying, for example, here, well, like when it comes to the hash value, you could use something like the MD5, or you could just do the encoding yourself. In this case, I would not recommend you use your own encoder. So this is something where this is how it would work, but it is useful to mention that it's better for anything that involves crypto. It's better to use like robust libraries. And then here, for example, they're setting up like a REST API to do this. So in this RESTful API, for instance, you're saying, uh, yeah, like you're basically saying here in this case, well, I want to paste some data. So this is the action I want to take. You're saying this is how long I want this paste bin to last. And then here's what I want the content to be. So in this case, like I made a mistake. This is not a URL shortener. It's a paste bin, which means it's just a way for you to store some text data. But a URL shortener would work in the same way. Right, and then the response here, so like for example, you would make a request and say, well, hey, I want to know what happens at this link, and then it would, let's say, give you what the content was and when it was created, and etc. uh, the analytics, on the other hand, is a bit is also sort of simple. Basically here it essentially has a reducer. I think that's the most important part, as in it just like sums up the values for each key, and that gives you a pretty good idea of how many users you have. So the last thing they talk about here is the scaling part. So we said here, like again, these are sort of a common trend, like a domain name server, right? So just like so people can access your website very quickly, uh, from textual description, right? Not just like an IP. The content delivery network, so you can just directly go to the object store and skip everything else. Otherwise, for any request that's not, think of this like as a cache, like for anything that's not in this cache, make a request to the web server where the server is like load balanced, and where you have a memory cache for everything, and you also have the underlying object store, which is also replicated. So this is gonna show up quite a bit, but there's, I guess, like a few. This is interesting, like a few talking points you can talk about. Like, well, should this be a key value store or a document store? Like, why not use a graph database? Why not use SQL versus NoSQL? And then in terms of caching, there's a billion ways of caching, from the caching client data on the browser to having cache at the content delivery network level. The database could be cached, and then the application could be cached, right? And then in terms of the asynchronous part, you have message queues and task queues. So there's all sorts of trade-offs here. And then I guess security. Let's see what they say about security. Yeah, this is a very famous chart, by the way. So this is very useful to just understand when should you when should you bother, right? So you should bother with branch misprediction if your queries take more than 5 nanoseconds in time, right? And then otherwise, same for L2, same. And then basically I think the main obvious thing here to think about is that anything that involves networking or disk is insanely slow. And notice like the difference between disk and networking. So it's 5x, right? But then here, for example, uh, here, where was it? So from SSD, already we're talking like it's 30 times faster, right, than disk, than HDD. That's why it's better to just have SSDs in general, although they're not as durable for like long-term cold data. But if you look at stuff like cache, like as in memory, like main memory is just way, way faster, and then it's crazy. So basically, I think the main thing you want to think about here is that disk bed and then networking bed. This is like another more visual explanation here. So yeah, for example, here, like in the case of Twitter, like let's say when you're writing something, let's say there's also going to be the read aspect. Uh, Here, I think the interesting part is the fan out, where like you're gonna basically have this fan out go to either a timeline service or notification service, etc. But it's also gonna send some data to like a Hadoop cluster. Yo, hey, Sudomaze, how's it going? We're talking about like basically prepping for system design stuff, and in general just understanding how this stuff works. I haven't done this kind of stuff in a while, so I just thought I'd refresh. um, yeah, so basically here I think the fan out service is a big deal. And then when it comes to here, like, and then Hadoop, you'll basically see with anything that involves like batch computation, which you can think of as being very useful in a couple of settings. So let's say the Twitter people want to, figure out like roughly their usage numbers. They'd have something like this, or if they want to aggregate some information for advertisers, like they would also have like some sort of batch processing cluster on the back end. It's interesting here, like they have tons and tons of blog posts that talk about how they do this. But again, the thing I want you to keep thinking about here is sort of here, like there's a sort of a common tricks, right? Like CDN, DNS, load balancers, memory caches, and database replication are ideas that show up over and over and over again. So make sure to commit them to memory because uh, I think that like okay, so a lot of times people say something like, well, like but it's a scale, and have you like made things scale or something like that? But what people fail to understand is at this point, like building this kind of architecture is really a drag and drop exercise in AWS, or it's like a config exercise, which is really equivalent to a drag and drop exercise, where you would basically say, well, I want 10 web servers, or I want as many web servers to handle the load that I have, in which case that's what the elastic part does. But effectively, it involves like duplicating stuff so that you don't have a single point of failure. But it also involves duplicating stuff so that you can take more concurrent requests at once. And so by those sort of two principles, like load balancing, CDN, memory cache, sort of all fit that framework, and is why like they're so often used. All right, so I think that was interesting. So let's look at mint.com. So I think it's a bit more complex. Uh, Not too much more complex though. So let's sort of think about it. So, like I said, like Mint is a popular personal finance app where you can basically connect your bank account, your investment accounts, to sort of keep track of what you have. There's also a few stuff that it does. It sort of categorizes transactions for you so that you can figure out like this is how much I spent on groceries versus movies versus fuel. And that also has a service that lets you basically recommend the budget, or you can hard set it. And then it sends you a notification when it has a budget. And we want this service to be very highly available. Um, so you can sort of imagine that, like, well, there's, like maybe you can let people set their own categories, but let's assume there's just 10, like, let's say, like housing, food, and gas. Then assume that we have all sorts of financial accounts, that this is how many transactions we have per month. And then we also assume that it's very, uh, yeah, it's very right to read heavy. Why? Because uh, when you connect your accounts, it's automatically itself going to be writing on your behalf. Like, okay, like I spent $5 on, I spent $10 on Thai food. I spent $20 on Steam. So these are writes that are happening organically by machine. So a lot of them are going to happen. But you're only going to visit the site like let's say once a week or once a month to sort of just make sure like am I on track? Did I spend too much money on stupid shit? Like what's my total net worth right now? So like you're going to be checking it more occasionally. And so each transaction, like basically at every point you have you're as a user, you're gonna say, like this is me, this is what I bought from this seller at this amount, right? And then if you sort of assume some amount of bytes for each one, even though like I think these would be hard to come up with on the spot, and then you can give an estimate for how many total transactions are happening per month given that you know how many users you have. So this is where the analytics service really matters, right? Like when you're figuring out like do I need to scale more, it's not enough to just look at like is my service down, yes or no. Like you have to have some sense of how many users do I have, how much data are they committing at every second, and then estimate that per month, and that in it of itself should give you a pretty good idea of uh, like how to scale your service. And I think this other really important idea here is knowing what your write to read ratio is. That way you can figure out like how well, you need to commit 10 times more service for writes than you do for reads. So it automatically tells you not just like in as a bulk, like how many servers you need, but just really per use case, how many do you need? So the way this sort of works is that you have an accounts API, right? So the way this works in Mint is that you would enter in, like, let's say, your banking credentials, and then your bank automatically, like basically Mint at this point, once you enter those credentials, anytime you make a new transaction, it would commit it to a queue, or like let's say in this case, this would be a fan out. So this is sort of similar. And then there's a couple of services that are each built independently, right? So there's the category service, there's the budget service, and then there's the notification service. So category, like what is this budget? Are you over or under budget? And the notification, should I tell this person yes or no? Right? Because people can change these. The other thing that you need to keep in mind is that like what does a transaction look like, right? So in this case, there's like a bank account, but the bank account also has a URL, right? So let's say chase.com, and then these are your specific credentials, and then a hash of your password. Even though I don't see why they need this here, this feels like a security risk. Your Mint user ID, which is the user ID under which all of your accounts are aggregated, and then when you made the transaction and what the transaction was, right? And then in terms of a RESTful API, what this would look like is that you're saying, okay, I want to post this data where I have this user ID, this account URL, and I want to commit it to this part of the RESTful API. So generally, I think that a lot of design discussions I've been in generally go here. And even though this is fairly basic, I think sort of giving a holistic idea is really good. That said, a lot of these questions tend to be very open ended. Like, let's say I told you, design the design Twitch where you have bots learning via reinforcement learning. Like this is an extremely open-ended question because then there's the game engine part, there's the reinforcement learning part, there's the Twitch part. So even when you're thinking of scaling, it's like which piece. And so you really need to figure out like what the person what you're talking to, like what they're specifically interested in. Or in your case, if this is a business that you're running, you need to figure out for yourself like which parts are the most important. So basically here, for example, like let's say the category service, like it's like like enumerate this enum. How do you figure out like what's the category here? Well, maybe you have like a list of specific vendors that are known to be of certain categories, so you'd have like a key value store, or it could be done like via machine learning. So let's say, or via just like like a rules engine. Like for example, like the user set markseraphim.com to be entertainment. Therefore, for any other transactions coming from markseraphim.com, those should also be categorized as entertainment. Whereas, like with the budget thing here, for example, the way they're doing it is you have a total budget, and then you allocate a percentage of your total budget to various categories. And if any one of them is exceeded, then make a notification. So this is the budget service. Uh, yeah. So in terms of scaling the design, notice there's no new ideas, right? Like I keep saying this. There's the DNS, there's the CDN, there's a load balancer. Everything here is like the reason why there's three rectangles because these are replicated. So again, replication, caching, queuing, are the main ideas that you need to think about. Again, why? Replication, you wanna don't want to have a single point of contact, and you want to serve more requests at once. Caching is oftenly made requests need to be faster than less oftenly made requests. And queuing is basically the way that two services communicate to each other in an asynchronous way. Right, and I think another here thing they're saying is that like make sure not to just jump directly to the design, so sort of try to see what your interviewer is interested in. But again, you notice that these questions can be uh, extremely open-ended. But if you sort of take it from the user's perspective, like, well, a user cares about these things. Now here's a service that does these things for them. Then the discussion becomes a lot easier. So I think I'll do like one last example, and I think we can call it a night. Uh, Pseudomaze, if you're on, you feel free to pick one. Otherwise, I'm gonna pick. Let's see, millions of users on AWS. All right. Okay. So let's see, what are they talking about here? So I think here the main difference they're talking about here is like all of this looks very simple, like same ideas: DNS, CDN, load balancers, replication, and the database, and at the process. Again, same idea. The difference here is like when they talk about auto scaling. So for example, like you could have a trigger that says once the like the let's say CPU utilization for the web servers goes beyond a certain point, or the average response time for a service goes beyond a certain point, then add more servers. AWS does this automatically for you, but you can sort of think of it like that. It's sort of like a if then else trigger. And even your replication, your auto scaling service needs to be replicated. Otherwise, it could also be a single point of failure, and then your thing crashes, like the whole thing blows up. So I think unfortunately this example wasn't very interesting. So let's pick another one. Let's say data structures for a social network, right? All right. So let's say with a social network, this is interesting, right? There's a, like you basically have a search API, and then you have a user graph service where you can either look up people, or I don't know what the person server here is. Uh, so again, like the graph, like the idea of a graph API here is figure out like when you think of a social network, it has a graph-like structure, as in not only is there a friendship graph, as in who's friends with who and who are they friends with, there's also an interaction graph, as in I wrote this post and this other person read it. And so could you share the repo? Yeah, so I'll be sharing the repo in the YouTube description from now on. I'm gonna make a habit of it. But it's called the System Design Primer by Don Martin, who's a tech lead at Facebook, it seems like. So I highly recommend. This is a really great repo, and you can see it's like shit tons of stars here. So very useful as a reference to review. And the reason I mentioned this is because if you look at like books, like let's say the coding interview prep books, generally they don't discuss this. Like what they generally do is that they tend to basically cover this part, right? Like let's see, let me show you. Like they tend to sort of randomly talk about just I think this last part here. They'll be like, well, you need to think about this thing, and you need to think about that thing, and this thing, and that thing. But the issue is like when you're talking to someone, to be honest, like they're gonna have no idea what the hell you're talking about because you're talking about too much shit at once. So that's why like I think structuring it on like graphically really helps, and then verbally talking about each of these components while remembering the main parts: CDN, DNS, load balancing, replication, caching, right? And then finally, talking about it from a use case standpoint, I think is like the most mature way to talk about it because it shows that you have the user's best interest at heart. You're not like just approaching something from a pure technology perspective. You're thinking who's using it, how often are they using it, how are they using it, what do they need to use it for. So yeah, I mean, I hope this was helpful. Like I said, this is a great reference that I highly recommend you check out. The System Design Primer by Don Martin. Other references that I very highly recommend are the Architecture of Open Source Applications, which gives you a good idea of how real systems work, not like hypothetical systems like Twitter and Instagram, because there's more systems than besides just Twitter and Instagram that exist out in the world that are very complicated. And then the last one that I recommend is Designing Data Intensive Apps by Martin Kleppman.